Hello and welcome back to the first season of the podcast For Code in Research, the companion podcast for the course on research programming in C++ from the Advanced Research Computing Centre at the University College in London. No discussion on C++ can be complete without talking about performance. And so for the 7th episode for the UCL course on Research Software Engineering with C++, my guest Klaus Iglberger and I will dive into the world of performance, what it means, how it can affect your code, and some practical tips we hope you find useful. Performance can mean a lot of different things to different people. To clear this up a little bit, Klaus Iglberger and I started our conversation about performance with this question. And for those of you who haven't been following the course and podcast shows so far, Klaus is an experienced C++ engineer, consultant and trainer living in Germany. So here's Klaus. What is it actually that we do mean when we talk about the performance of an application?
Usually we refer to the runtime performance. So the time some executable needs to perform a task, the faster the better, of course. We might also a little bit in the background include the information of how much resources it takes. Less resources is good, of course, but usually time to finish the executing is what we mean with performance. Sometimes the definition is a little different. In a computer game, for instance, performance is potentially how many frames per second a computer game can compute. Then, of course, it's the overall experience, the smoothness of the image, etc. All of this, I believe, is part of the performance term.
But also the resource usage, in particular the memory usage, is also an important part of that. Yeah,
absolutely. Now, of course, it depends. Sometimes we have to do compromises, and I'm sure we are going to talk about this. So once in a while, we use a little more memory to gain performance. Sounds counterintuitive, but indeed, sometimes this may be a solution. But still, overall, we try to reduce memory consumption and memory usage, also transfer of memory from the main memory to the CPU core in order to gain runtime performance.
And when we look at a computer program, is there a way that we can assess, before we even run it, how performant it could be?
That would be amazing, but unfortunately, I'm not really aware of how that should work. And quite honestly, this is what I usually do with my students in my training classes. We are very bad at performance guessing. We might see a couple of versions of a piece of code, and then looking at this, we are so certain that this particular version is the fastest. And then when benchmarking it, really running it, realize that it's actually not so good after all. So our gut feeling in terms of performance very often is pretty wrong. And therefore, if you really want to know how fast it is, the one thing that you should always do is to benchmark it somehow. To get a real number, how many seconds it takes to execute the thing, how many frames per second you can compute, something like that. I think that's the only real metric.
As Klaus mentioned, when we talk about performance, we usually mean the time it takes for a program or a particular execution of code to finish, and how much memory and other resources it will take. That's not an exhaustive list of definitions for performance in computing, though. You could also consider, for instance, how much time it takes for your code to build, something Klaus and I will return to a bit later. But it could also mean how long do your tests run. Some also include measures such as how many bugs are found in the code and how long does it take to fix them. So performance has a lot of different phases. But in this episode, Klaus and I want to focus on time of execution and a little bit on memory usage and its influence on how fast your code will run. As Klaus and I said, you can't tell for how long your code will run and how resource intensive it is by just looking at it. You need to measure it. And we're going to cover this a bit later. Still, there is one technique that is sometimes used that allows you to get an upper limit of how many times a particular piece of code is being executed, and it's called the big O notation. And here Klaus and I talk about it in a bit more detail. But there is something called the big O notation, which is usually to assess how efficient, how an algorithm is being computed in terms of how many computations are being done,
Yeah.
So, but could we perhaps expand a little bit more on the big O notation and the kind of role it could play in making your code more efficient?
I think this is something that everybody should know about, but it's not something that everybody should take too serious. Of course, there is a lot of value to that, but it's not the ultimate answer. The big O notation comes from theoretical computer science, and it kind of gives you an idea of how well an algorithm scales with an increasing number of elements.
Mm-hmm.
Kind of lowest O that you get is O1. So written in O, paren 1, paren closed. O1 pretty much means that the execution time is constant. So if you increase the number of elements by 1,000, still it runs at the same time. You can already imagine that this is not something that we'll get often. What is much more likely is something called ON. So if I have 1,000 more elements, it takes 1,000 times more time to execute something. So classic example is a find algorithm. If you have 1,000 elements, you'll find it in some time. If you have 10,000 elements, it takes 10 times as long. On average, though. Of course, I may be super lucky and find the element in the beginning. One hit and I have the right thing. But if I'm unlucky, it might be the last element in a collection, and then I have to go through all the elements. And of course, this takes much, much longer. What I want to say here is that ON is a statistical measure. The real thing, of course, may be different. But on average, if I do many, many, many runs, I have a linear relation between the runtime and the number of elements.
And I think that's quite important to note that it's not really, it doesn't give you the exact number of computations that, because as you say, you may find the element that you're looking for in that array or whatever right at the beginning. Right? But it's the maximum time of computations that you can do.
Perfectly said. Indeed, the maximum time and the scaling behavior. This is what the big O notation is about. Not really any runtime. Of course, it could be bad. It could be an ON square algorithm. This is something that scales quadratically. So if I increase the number of elements by 10, the runtime increases by a factor of 100. That's not great.
That sounds something like a nested loop, for instance.
Yes, exactly. So I was about to say this is what the matrix vector multiplication, for instance, is. If the matrix grows by a factor of, so the number of rows and end columns grows by a factor of 2, the overall complexity is a factor of 4. Of course, it can be even worse. N cubed, that is what a matrix multiplication is about. This is why this is such an expensive but important operation. And there's also exponential growth, which is bad. But then there's also some things in between. For instance, between O1 and ON, there's also O log n. If you increase the complexity by a factor of 100, then the number of elements, the runtime might only increase by a factor of 10. This is good, but again, something that you do not often get. And sort algorithms very often have an n log n. So there's somewhere between ON and ON squared.
Right.
So your goal now is to pick an algorithm that has a low complexity. So a low big O notation. This would be great, but sometimes there just isn't an algorithm that improves the compute time. Just as an example, talking a little bit about my experience, I mentioned the matrix multiplication. And there are actually algorithms that have a lower complexity, that do not have the complexity of n cubed, but something in the range of n squared and a little bit. And still, these algorithms might not necessarily run faster in practice, simply because they might be a little more complicated to implement. They might require much more memory. Of course, it slows down the machine. It very much depends. So it's not just the big O notation, but yes, of course. In theory, choosing a better algorithm with regard to the big O notation makes your program faster.
And I think that takes us back to a discussion we had about libraries the other week. You mentioned sort and find, right? You can sort of implement the code yourself, but I think there are a number of libraries now out there that usually implement very efficient code in libraries.
I know that some people prefer to write this stuff on their own, but from today's perspective, please don't. Sort and find is actually part of the C+ standard library already, so you'll find them in the algorithms section of the standard library. The algorithms header contains all of this stuff. Don't write this yourself, reuse. This is so much simpler and faster and more correct too. Multiple advantages.
The big O notation is, as we said, a theoretical model to calculate or at least to estimate the complexity of mathematical expressions and algorithms. Getting a grip on the complexity of algorithms has occupied the minds of great mathematicians throughout the ages. And the notation we know as Big O seems to come from the late 19th century and two German mathematicians, Paul Bachmann and Edmund Landau. And its aim was to put a limit on a mathematical function when the value of the arguments used in the function grow, and in particular when they approach infinity. For computing, people started to look into this very early on in the 1960s, and perhaps for obvious reasons. If you can put an upper limit on the calculation complexity of a particular function, then you get an idea how expensive it will be in terms of runtime and resource usage. It won't give you an exact value though, because as Klaus just said in the example of the find function, the actual execution of the code may actually take a lot less. Also, the actual time the computer takes to run it will vary as it depends on the hardware. Still, as a theoretical model, it has its uses, in particular when it comes to designing and creating new algorithms or estimating old ones. And of course, another reason seems to be teasing students with exam questions or making engineers sweat in job interviews. In my career, I had my fair share of them when I interviewed for jobs, let me tell you. I'm still having flashbacks. But let's leave the theory behind us now and turn to the more practical aspects of performance and performance measurements. Luckily, there are a number of tools out there, and Klaus and I are discussing some of them now. I would like to move on to how we measure things. So we don't know upfront. So we look at a piece of code, we don't know how fast and how memory intensive it will be. We can make some educated guesses, but there won't be much more than guesses.
True.
So we need to measure. So how can I measure this? And what kind of tools do we have that allow us to do that?
Yeah, there's numerous tools. Yeah, of course, because it's such an important topic. Because people that listen to this might not have a lot of experience with C++, they might actually appreciate an online tool. So there is an online tool called quickbench.com, quick-bench.com. This is actually a pretty simple, a pretty useful online benchmarking tool. So what you would do is you would write, say, an algorithm, but potentially in 2 or 3 or even 4 versions. You could mark them accordingly. You could say this is the first, second, third, fourth version, and then this tool would benchmark them separately. And that tool would take care of a lot of the details. It would run this, of course, somewhere in the cloud, and I don't know where exactly, and it would collect the results and display them in a nice form. Now you know which one of your versions is faster, or if there's any winner at all. That's super useful. If you go there for the first time, there's actually an example that should pretty nicely explain how it works. If you still have questions, all of this is based on Google Bench. So if you search for this in your favorite search engine, you will actually find a nice documentation explaining all the little details.
Is it a Google tool?
So the QuickBench is not necessarily a Google tool. I don't know exactly who hosts it, but it is based on the Google Bench tool. Yes.
Oh, right. Okay.
There's various more professional tools to do things locally. So on a Linux system, there is gprof, which is just short for GNU Profiler. And this is a tool that you can use to profile pretty much all characteristics about your program. Yes, of course, you could use this to just benchmark the time. But this tool also collects information about cache usage, memory usage, of course, in general, main memory, but also the different levels of caches, translation look-aside buffer misses, and so on. So many little details that might indicate why a program is not fast enough or why it is fast. So perhaps one program is faster because the number of cache misses is just lower.
Right.
We are already starting to talk about some advanced topics. So universities usually offer courses to teach how to optimize for cache locality and for proper cache usage, etc. Quite an advanced topic indeed.
Okay, let's not go there just now.
Another tool that is very commonly used called Valgrind. Valgrind is a memory simulator, to say it in a simple way. I can use this to try to optimize your code with regard to memory usage. There's also a cache grind and call grind subtool that again allow you to very, very in detail analyze how the code works. Where are the bottlenecks? Where are the parts of the code that are most expensive? And I'll come to that in just a bit because I believe this is a central part. And I should also mention a commercial tool. So if you can afford it, Intel has the so-called vTune profiler. That is also a tool that gives you numerous information about the individual characteristics of your executable.
Right. Okay.
There is many tools, and if you again do a search online, you'll potentially find more, probably potentially even many more. But now here comes an important point. You cannot and should not optimize the entire program. That would be too expensive, time-consuming, and you might not gain a lot. Imagine that there is one part of your executable that takes 80, perhaps even 90% of resources, the compute kernel. But if you now waste time on the 10 remaining percent, the best, and truly the best that I can achieve is an improvement of 10%. So I might have spent a lot of time and money pretty much optimizing the wrong part. And so the first thing in any benchmarking, you try to find the core of your resource consumption. Where are the cycles spent? Which 10%, perhaps 20% spent the most? And this is the part that you should optimize.
I think that's quite an important point. So it not only gives you the information about how your code performs in terms of time and resources, but also helps you identify what to focus on next.
Exactly. Where is the bottleneck? Why is my program not fast enough? There's always a reason. And you find that reason, this is the next thing that you should consider for optimization, because the rest will not buy you as much.
So at what stage would you then run these profiles? I think they're called profilers generally, aren't they?
Yep.
So at what stage would you run them? Would you always run them? Would you run them at build time? Could you integrate that, say, when you do a GitHub action or things like that? At what stage should you do that?
Usually they're used on the final executable, the thing that truly runs. And of course, the executable now should be built for performance, should be built for speed. It works on the executable. Not right away start to optimize though. No. I believe there's so much more important details about your program. So first, it needs to be correct. So it sounds so trivial. It almost sounds stupid. But,
it would help.
It is way easier to make some simple code correct than some highly optimized code. Optimization usually makes things a little more complicated. So first, make it work correctly. And then afterwards, you identify the hotspots and optimize those. And so I would not start with optimization, not really. I would first, as simple as possible, write the code in order to have something that I can also build on. Perhaps there is no performance issue. Perhaps it's fast enough already, and you don't have to do anything right now. But if there is a performance problem, or there is a requirement to make something fast, then you start to profile and optimize.
Okay. Klaus mentioned a number of performance measurement tools, and you'll find the links to most of them in the show notes. Sometimes you can also do a quick check on performance without any of the tools and simply using functions from the standard C++ library. In the C++ 11 standard, a new time-measuring API was introduced called Chrono. But before we get carried away with tools, bells and whistles, let's remember what Klaus also said. You don't start with optimizing your code. You start with getting it right in the first place. And that includes having tests like unit and integration tests, so you can spot any bugs before they get buried in your code later on. Also, the C++ standard library comes with a ton of functions and tools, many of which are optimized already, so you don't have to reinvent the wheel and design your own sort, merge or find algorithms, for instance. Of course, at some stage you may want to look into how you can make your code faster. And this is not only a question of how efficient your algorithm is, but also down to how your program uses resources, in particular memory. Modern operating systems go quite a long way in optimizing memory handling and getting your data in and out of the different memory locations. But even then, if your program starts leaking memory left, right and center because tons of objects get created but not cleaned up when they're no longer used, well, this can bomb the performance of anyone's program. I included a link in the show notes with some recommendations on how to improve memory usage in C++, and I hope you take a look. One tool we haven't mentioned so far when it comes to performance improvements is the compiler. C++ compilers like the GNU compiler come with options for optimizing code, the so-called optimization flags, and they can indeed help your code run more efficiently. But not under all circumstances, as Klaus and I mentioned in this part of our conversation. And you already mentioned the keyword that I want to talk about next, which is build, because you can actually optimize code when you build it. The GNU compiler, and I think pretty much any C++ compiler, or at least the big ones, have optimization flags. So what actually do they do? And what different levels of optimization do they offer?
The levels are a little different for every compiler.
Mm.
Every compiler vendor has its own flags to some extent. On Linux, again, talking about perhaps GCC or the client compiler, they have similar flags. There's the -O flag. The O is just short for optimization. There's a level 0, which essentially says, please don't waste time on optimization. I just need it to work. I just need to run it. Produce the first thing that you can get. From there, O1 means do a little bit of optimization. O2 then means, okay, do a little more optimization. And basically you tell the compiler to just use more time, sometimes it truly is much more time, on trying to optimize code, optimize loops, roll out loops so that you don't have any loop overhead anymore, etc., etc. And usually the maximum is O3. The sane maximum is O3, which then basically says, okay, compiler, I give you all the time in the world, make it as fast as possible. So I said sane optimization. There is also some flags that go beyond this.
Insane.
Insane. So there is O fast, for instance. The -O is small fast. That, however, means that you allow the compiler to do optimizations that might now actually reduce correctness. And that, of course, already sounds suspicious. So this is something that small portions of code might use for a reason where you know that it works, but of course not for the entire executable. No. Again, the hotspots, they should be optimized. The rest doesn't need an O3 and most definitely nothing beyond this. So a very reasonable level is O2. That's perfectly enough. And actually, in most cases, is already the fastest you can get.
Okay. So you can actually check that then if it makes any difference if you compile with O2 or O3, leave alone O fast.
You will actually realize there's a difference. First, in compile time, it takes a little longer. But then also take a look at the executable itself. If you compile with different optimization options, you will find that the executable might get bigger. And it might get bigger, for instance, because the compiler now starts to inline more aggressively. Inlining means that I take a block of code, usually a function, and put it where the call would happen. So instead of doing the interaction of jumping into another section of the executable to that function, I have the code right in line where I would call it. Makes a big difference in performance, sometimes a huge difference. But of course, now I have duplicated the code and this bloats up the executable at least a little bit. You should not say it does, it might. There's functions that are so small that they actually might even help to reduce the size. But this is the functions that a compiler might even on its own inline, you might not have to do anything here.
But I think that's quite a good point because the downside could be that the compile time goes up. And, for smaller programs that may not be that essential, but for larger packages that may actually be quite a stumbling block, particularly if you want to find out if your build works, etc. And then it takes a few hours. And the other one then is that the executable itself may grow beyond a reasonable size, shall we say.
Yep.
So going for higher optimization flags is not always better then, is it?
Not necessarily. It also depends on what you do, on what you run. So O3, for instance, the maximum I described, the compiler might try to optimize for certain data sizes. So for instance, it might optimize for vectors that have at least 1,000 elements. And for that reason, it might now produce certain sections in the code where loops are unrolled by a certain factor, a factor of 32 or even 64. That does not pay off if you have a small data set, though. If you have only 10 elements, any optimization for 64 elements doesn't happen for you. So the executable is bigger, but you don't gain anything. And so this optimization is wasted.
Okay.
I should mention at this point the tool Compile Explorer, which I believe every C++ programmer should know. So godbolt.org. This is where people find Compile Explorer. In Compile Explorer, you pretty much see what code the compiler generates. So on the left, there's the C++ code. On the right, you will see assembly code. And that code changes based on the flags that you use. So if you give an O1 flag, the code is potentially still small. But if you now use O3, suddenly there's much, much more code. A factor 3 to 4 sometimes. And the reason simply is that the compiler tries loop unrolling and inlining more aggressive, etc., etc. And you might realize, okay, this special case actually doesn't apply for my problem. Then you've lost performance, at least potentially.
Now, I don't know about you, but I'm always interested in finding out how things actually work. So having a tool that can show you the assembler code of your program is a great way of understanding not only what your code actually does, but also what C++ compilers do under the hood. So I do encourage you to check out the tool Klaus mentioned. You find the link to godbolt.org, a funny name that, in the show notes along with all the other tools mentioned in this episode. In the last part of my chat with Klaus, I wanted to pick his brain how he used optimization in his own work with C++, and also touch on an aspect of C++ performance for an area of computing that we will touch on in the last part of this course, and that is parallel computing. So here's Klaus again. Do you have an example when you yourself experienced some kind of performance improvement and how you approached that in some piece of code that you worked on?
In the past, I've written a math library. And when I say math,
as one does,
linear algebra, it's all about performance. That's the whole reason it must run at peak performance. And so in this library, my major endeavor was to try to find the best algorithm and the best implementation of this algorithm for a certain data set, matrices, vectors, etc. I've spent a lot of time optimizing various tricks, from low-level stuff like SIMD operations to more high-level stuff in trying to structure the code such that the compiler can optimize it a little more aggressively on its own. Yes, if you do things properly, in this particular case, I would gain massive performance improvements, which is exactly what people want to hear in C++. I've not mentioned yet, C++ is a very performance-centric programming language. So, therefore, it's perfectly reasonable that we talk about performance.
Yeah.
So if in C++ we have to make a decision, should we favor this because it's faster or that because it's safer? Usually we favor the performance side. But with a reasonable argument, because it proves that you can always make fast code safe by just wrapping it somehow, by putting something on top of that. But it's pretty much not possible to make a safe code fast because you've already lost the performance on a lower level. So
Right.
Based on that attitude, C++ is indeed very performance-centric.
The one thing that we haven't touched on, which actually is going to happen only in the next few classes when we talk about parallel computing. So far, we talked about code that runs on your machine, right, which is not an HPC cluster. Well, sometimes it is, depending on your problem. But let's say I compile and build a software that runs on my laptop or my PC or whatever. But what kind of extra dimension in terms of profiling and performance do we get when we actually go to something like a supercomputer or a high-performance cluster? I think I know this is a very vague question, isn't it? It's like asking how long is a piece of string, but yeah, I'm asking it anyway.
But it's an important question. You will probably not find any CPU or even a small piece of hardware anymore that is not in some way parallel. Parallelization is indeed what has gained the most performance benefits in the last couple of decades. I mentioned SIMD, which is some kind of parallelization because inside the CPU, we do not just compute a single result, but multiple results in just one instruction. A single instruction for multiple data, parallelization. And of course, we have multiple cores nowadays.
Yes.
Not just 2 or 4. No, we have 32 cores once in a while, depending on how much money you have. And of course, you could use all the CPUs to produce results much, much faster. So now the extra dimension that we get, of course, is now the hardware dimension of how do these cores, for instance, share the memory. If all of these cores need to access the same piece of data in the same memory, that may be a bottleneck. And that's then something that, again, algorithmically, I have to deal with somehow. Suddenly, of course, I also have the problem of parallelizing at all. How do I parallelize an algorithm on a large data set? Potentially, it's trivial. Perhaps I just have to compute the first part on CPU1, the second part on CPU2. Perhaps it's much more tricky. And so suddenly, optimization is also thinking about how to separate, how to distribute the work onto several work units. And this is tricky. I have to admit, this is probably one of the most tricky things that we do nowadays, concurrency. And I don't know if there's anyone alive that really understands concurrency, but my personal impression is you just need to get a lot of experience. Eventually realize, okay, this works and this does not. And you also develop this gut feeling. And I know gut feeling is not good, but still, this little bit of gut feeling that tells you, okay, this is where I have to pay attention, or I rather do this because else it might go wrong. It is very difficult.
And that puts the magic back into computing, doesn't it? A little
Absolutely.
bit. Well, thank you very much for your time, Klaus. I'm not going to dive into parallel computing too much at this point. In fact, This will be the subject of next week's episode, where I will meet with Mark Hartung from Dive Again, the company in Berlin, Germany. Mark is having extensive experience in parallel computing, and I hope you will find this introduction to this fascinating but also difficult subject helpful. But before I end, and as per usual, here are 2 quiz questions for you. Number 1. Memory leaks can slow down your program. And my question is, how can so-called smart pointers help you to avoid leaks? And question number 2. You have 2 loops, an outer loop, one that is running inside it, that is a nested loop. In the big O notation, what is the cost of this nested loop operation? And is there a way in which you can optimize it? Have fun with the quiz questions. And finally, I'd like to thank Klaus Iglberger for all his time and patience in talking to me about C++. I know how busy you are, Klaus, so this is much appreciated. We're going to hear from Klaus again in the final episode of this course in a few weeks' time. But first, see you all next week when we talk about parallel computing. You will find the material for this course on the Moodle platform at UCL. This podcast is produced by Peter Schmidt. The music comes from Daniel Lindenblatt in Berlin, Germany. And finally, thank you for listening, and I hope you enjoy the course. And with that, goodbye.